So what was the answer in cylindrical coordinate? I think first you have to write dr, h1 du1 e1 cap, h2 du2 e2 cap plus h3 du3 e3 cap. What are h1, h2, h3? In case of cylindrical coordinate, 1 row 1, am I right? 1 row and 1. So now that's why dr would be, so 1 du1 means first coordinate was row, am I right? Row into, sorry, d row, du1, d row into row cap plus row d phi, row d phi into phi cap plus dz into z cap. Once you find velocity by dividing this one by dt, dr by dt is equal to rho dot rho cap plus rho phi dot phi cap plus z dot z cap. V rho is equal to rho dot, V phi is equal to rho phi dot. So Vz is equal to z dot. Square and add them, you will get so total velocity, square of the velocity. Am I right? Yeah, we need this one because square of the velocity will come in kinetic energy part. Am I right? We had two basic principles here. So that is the starting point of your Lagrangian mechanics actually. So one is D'Alembert's principle, and other one is principle of virtual work. We shall see what are those. Okay, I mean qualitatively. Yeah, first one is I have forces that are applied on the system. Okay, let me take the situation. So let me just divide my forces into two parts. Okay, Fi, I mean force on ith particle, because usually we try to generalize the theory. So isn't it? I mean, so if I take n particle system, so I'm not saying what are the number of particles. This force on the ith particle. Is that okay? Force on the ith particle we are going to divide into two parts. Okay, so one is applied force, other one is constraint force. Applied force, this A stands for applied force, other one is constraint force. So Fi, small f is constraint force. I mean, so you may have the condition that interparticle distance constant, or you may have something so which causes this force. I mean, that is this will cause that constraint. Okay, whatever the constraint that is caused by this force. So now, so force is divided into two parts. Now, usually we are going to divide. So we are going to define one thing here. What happened? Call. Yeah. So look at here, at equilibrium, what would happen? What do you mean by equilibrium? Net force equal to 0, am I right? Net force equal to 0 is the equilibrium situation. At equilibrium, so I can just write this equation. So Fi, since net force is 0, work done is also 0, am I right? Whenever force is 0, work done is also 0. Fi dot delta Ri, So I mean this is again your displacement of the ith particle. Is that okay? Usually we call it as virtual displacement. Again, so let me call this one as displacement of ith particle. At equilibrium, this should be 0. Is that okay? So at equilibrium, so this should be 0. So again at equilibrium. So now I am going to divide this one using this one. So this is net force, okay? This is net force. I am going to divide this one into two parts. So what is that one? Fi applied plus constraint force plus constraint force. So dot delta Ri is equal to 0. Dot delta Ri is equal to 0. Usually this delta Ri are called as virtual displacement, okay? I think we need to study still more theory to understand this 100%. Let me give some logic behind this one, okay? What we are doing here, what we are transforming here, like that, okay? Now, once we get this situation, what we do here is next one, we restrict ourselves to this situation, like that, okay? Look at here, we restrict ourselves so to the system, where net work of forces of constraint is 0. Let me tell you how it happens, okay? Net work of forces of constraints constraint is 0. I mean when I divide this one into two parts, summation over Fi applied dot delta Ri, so plus summation over I, so Fi dot delta Ri is equal to 0. We restrict ourselves to the situation where this part is 0. So let me tell you how. Suppose with gravity, if you just drop one object, it will fall down. So am I right? So now if you want to hold that one, so I mean, so you can place that one on a table, am I right? You can place one mass on a table. Can I do that one? Mass M. Now mass is mass can move only in so 2 dimension on the table, am I right? So are you getting my point? I have gravity. Now something is restricting mass not to move vertically downward. Am I right? That's a constraint again. Yeah, so it is there in the book. You make it very brief. So I have gravity. So now due to that gravity, I mean I'm doing something, I'm just restricting that one. So something is restricting that mass not to move vertically downward. What is that? Normal reaction, am I right? So normal reaction is restricting that mass to not to move vertically downward. Am I right? So now look at here. So its motion is confined to table, plane. Am I right? Once if it moves on the table, now look at here. This is force of constraint. This is your F, and your displacement is always perpendicular to F. Are you getting my point? So after you impose that constraint, when you move that one, so your displacement is always perpendicular to that forces of constraint. So in most of the case, this will happen. Is that okay? So that's why we are restricting ourselves to this situation. That means this cover lot of system actually. This cover so lot more. So I think so there are no other cases where that will not happen usually. Okay. So now we are restricting ourselves to this kind of situation, and the same thing will happen in many cases. Is that okay? So now suppose if you take so pendulum, what would happen? What is the constraint here in pendulum? Length equal to constant. What causes that length equal to constant? Tension in the thread. Am I right? So that will make this length equal to constant. Otherwise, it would have extended or contracted. Am I right? So the tension, look at here, when mass moves here, look at here, this is always perpendicular to its velocity or displacement. Is that okay? In most of the case, that will automatically happen, but again, so while solving, we will not quote, okay? So I'm just discussing the theory here. While solving, we will not quote that one. Is that okay? So now, next one. So we restrict ourselves to the system where net work of work due to forces of constraint is equal to 0. Is that okay? So then, for condition for equilibrium, what is that condition for equilibrium? Condition for equilibrium, that's equal to summation over I Fi A applied force dot delta Ri is equal to 0. Remember, if we went for Newton's second law, we need this one also. We need this one also. In our formalism, we started with that virtual work. We call this one as actually total virtual work, okay? Virtual work. We call that one as virtual work. So in this formalism, so we started with this one. We haven't started with Newton's second law, remember. Is that okay? If we start with Newton's second law, again, you need to take care of again all forces in that one, isn't it? So now here, yeah, we have constraint here. Now look at here, in this equation, so this part is avoided. Forces of constraint is not appearing in our equation of equilibrium. Is that okay? Usually in Newton's second law, you have to take everything, am I right? But in our equation, again, our equation is not concerned with the force, it's concerned with the work done. And in that one, there is no forces of constraint because we are restricting ourselves. And in most of the situation, that will definitely happen. Is that okay? So forces of the, work done due to forces of the constraint is always 0 usually. So that's why, yeah, this is for equilibrium, but if masses are stationary, if they are equilibrium, we are not worried about this one. And we need to study dynamical case, am I right? So that's why, again, we will just extend this one. So we will just extend this one. The extension is done in that case. So look at here, for non-equilibrium condition. For non-equilibrium condition, ultimately, I told in many problems, forces of constraint may not be known. So known quantity, remember. So that's why we need to avoid that one. So our ultimate aim is to avoid that one, remember, okay? So it should not come into our formalism. Is that okay? Into our formalism. Now look at here, next one. For non-equilibrium condition, so we call this as D'Alembert's principle, okay? We call this as D'Alembert's principle. So I can say like this, Fi applied, actually it should be written like this actually. Fi is equal to Pi dot rate of change of momentum. Am I right? So can I write like this? Again, that's also vector. Fi is equal to Pi dot. So now Fi can be written as, how do you write? Fi applied plus forces of constraint. Am I right? Is equal to Pi dot. So Pi dot Again, let me just substitute this one. Let me just substitute that one here. So what would happen? Again, yeah, wait a second. Now let me take it like this. Here I have taken the situation. So how I concluded this one actually? This equation? Because I have taken the equilibrium, net force is usually 0. Am I right? Net force is usually 0. So now look at here. So in this one, which is 0? Not this net force, Fi applied plus Fi vector minus Pi dot, this is 0. Is that okay? So now what I do here is I am going to take the same equation. So this Fi dot delta Ri is equal to 0. Again the same step, but this part becomes 0. Why? Again, so forces of constraints are non-zero, but work done due to that one is 0. Because displacement of the particle is always perpendicular to the forces of constraint. Again, I can write the next step like this. Look at here. So Fi applied plus Fi minus Pi dot delta Ri is equal to 0. And the resultant equation by taking this part 0, Fi dot delta Ri. So by taking that part 0, look at here. So it is there in book, make it brief. So ultimately your equation would be like this. Fi A minus Pi dot delta Ri is equal to 0. For dynamical case, non-equilibrium case. And that's very important equation where our forces of constraints are not appearing in this equation. We call this one as D'Alembert's principle. D'Alembert's principle. D'Alembert's principle. By directly taking work done, we achieved one thing. Again, if we went for force formalism, we need to take all forces whichever appear in the system. By taking work done, we could able to eliminate what is that constraint force. I mean, so contribution by the constraint force. Is that okay? It's in our equation. So now we call this equation as D'Alembert's principle for dynamics. Is that okay? Now look at here. So our next aim, again I need to define something here. So there will be constraint, am I right? There will be constraint. Usually due to that constraints, so these coordinates are dependent actually. Is that okay? Due to that constraint, those coordinates are dependent. Again, we are taking the system with constraint only. So since those coordinates are dependent, we can't write this one equal to 0. So directly we can't write this one equal to 0. Look at here. So this Fi minus Pi is not 0. Is that okay? This will come actually, and we don't know that one. We don't know that. Okay, that's why. So our aim is to transform this equation so that whatever the coordinates you have, those are linearly independent. So that you can put this part equal to 0 actually. Are you getting my point? So so when you have trivial solution of some linear combination, when all are linearly independent, am I right? Suppose I'm taking it like this. Suppose what is the example for? Again, it's a kind of combination, am I right? It's a kind of linear combination. Now let me take the situation like this. Suppose ax plus by plus cz is equal to 0. Actually, I need to derive this one to explain it completely. Yeah, ultimately, let me just make it brief here. Ultimately, our aim is to make this, these coordinates, what you call, independent of each other. So one should not link with other. So just like yesterday I tried to explain, so how in case of constraint, one coordinate is related to other coordinate, am I right? We need to avoid this situation. That is nothing but our transformation to generalized coordinate. Usually we start with our Cartesian coordinate, am I right? After applying constraint, we will transform that one usually. So we say Ri, it is transformed to generalized coordinate Ri, Q1, Q2 and so on to Qn, sometimes T. This is a transformation equation. Transformation equation is, suppose if you write x equal to r cos theta, y equal to r sin theta, am I right? That's actually transformation equation to other coordinate. Is that okay? Now look at here, I have taken n coordinates, am I right? I have taken n coordinate. What is that n now? So these are generalized coordinates. Now let me say Q1, Q2 and so on to Qn are generalized coordinates. Then how many generalized coordinates there will be? 3n minus k. So am I right? So k number of constraint. If you have k number of constraint, and we are going to transform our coordinate like this. Again, we need to take example, otherwise you can't understand. So then we will transform into generalized coordinate. This is our transformation equation, the representative of transformation equation, just like this one. Usually our transformation equation will not contain time, okay? Very rare case. So now n is equal to, what is that n? n is equal to 3n minus k, am I right? K independent constraints, and there will be k constraint equation. K number of holonomic constraint, okay? That I haven't mentioned here. K number of holonomic constraint which will reduce number of coordinate required. Once you go for this generalized coordinate, now you have to derive much more actually here. So what you can do here is, look at here. So what you can convert this equation is, you can convert that equation into, again that is the derivation of Lagrange's differential equation in one way, okay? So there are many ways of deriving that one. So again, so using this equation you can define dri, because that's a function of all of these, just like our chain rule. So again proceeding with that one. So it requires some effort. Now just let me write this one. This equation can be transformed into this type, okay? This type that can be written like this. Look at here, summation over j, summation over I, because so summation over all particles in the system. So d by dt of dou t by dou qj. Qj is generalized coordinate. Wait a second. Qj dot, not qj. Dou t by dou qj dot. Dou t by dou qj dot minus dou t by dou qj. So minus dou t by dou qj. So let me put it in bracket. Let me write what is this, okay? Let me write what is this. Minus qj not over dot, usually dot product will go actually. So when we do that one, delta q, wait a second, delta qj, wait a second, delta qj summation over summation over j only, sorry. Now I will not be there, look at here, I will not be there. Ri was corresponds to, so remember, whatever the coordinate we have written, that is for whole system. Are you getting my point? Now, earlier we had, so first particle, second particle, like that. After constraint, look at here, we are talking about these coordinates actually. After getting into generalized coordinate, we are talking about this number of coordinate, and we are making the summation over that one. J is equal to 1 to n. So, this is the transformation, that is the derivation actually. Is that okay? So, now look at here, this is equal to 0, this is equal to 0. This is D-Elmer's principle can be transformed into this kind of equation. Once you transform it into this kind of equation, look at here, this delta Qj, so this is a summation, am I right? This is a summation, this is a kind of linear combination. Then these all are independent and non-zero. These all are independent and non-zero. Then what would happen in this equality? This part should be 0. So we can't write the same thing here because these are dependent. Is that okay? Suppose delta R2 depends on delta R1. So delta R1 is equal to 2 times delta R2, suppose. Then that becomes different, am I right? So in that case, you can't write coefficient equal to 0. Now you have these all are linearly independent. In this summation, in that linear combination, these all are linearly independent. So that's why, so this part you can put it 0 because this cannot be 0. Okay, this cannot be 0, then this part should be 0. Okay, so that's why our transformation is into linearly independent generalized coordinates, so that no more relation between the coordinate exists. Once we do that one, then only we can put this part equal to 0, and that is our, look at here, d by dt of dou t by dou qj minus qj dot dou t by dou qj. So that's equal to, that's minus qj, capital Qj. Let me define what is this one, is equal to 0. Is that okay? So now look at here, there are n number of this kind of part in this summation, and each of them are individually 0. And you can put that one 0 only when these are independent. Is that okay? Where j equal to 1, 2 and so on up to n. N generalized coordinate. There will be n generalized coordinate, n differential equations like this. Yeah. Over. Our aim is to, now look at here, these are dependent or connected by constraints. Equation. So now these are independent. Is that okay? So that was our aim, so that we can put this part equal to 0. That becomes equation of motion actually. Is that okay? In generalized coordinate. In generalized coordinate. Now, so look at here. I need one more part. What is this qj? Am I right? So for that, I need to do some derivation here. Not much needed. Now let me take this one. Summation over fi dot delta ri. So this was our what you call. Usually this is applied force, okay. So now onwards we will not write that A, okay. So in future we will not take that force at all anymore, yeah. Which one? This one? So wait a second. We are transforming this equation, the derivation is there in Goldstein, okay. So better to refer Goldstein. We are transforming this equation using this kind of equation. That's our transformation equation to generalized coordinate. In this one, these are dependent because of constraint. That's why you can't put these things individually 0. Now in this summation, so these delta Qj cannot be 0 and they are independent. That's why this part can be 0. Is that okay? Usually, how do you define linearly independent thing? How do you define linearly independent thing? Usually vectors, in vectors we have done like that one, so that only trivial solution occurs. Am I right? So summation over, so ai into I, that's equal to 0. That kind of relation can happen only when all ai are 0. Am I right? You have written like that. Then we say these vectors are linearly independent. I am talking about similar thing. There is no relation between this delta Qj. So any of those things. I mean, there are n of this type. So there are small n number of these things. So there are no relation between them. So that's why this kind of relation can happen only when all individual coefficients are 0. Same situation. Again, I am not deriving this one, okay? I am not deriving this one where j is, so Qj is our generalized coordinate. I am just writing this one as generalized coordinate. We shall apply this one, okay? We shall apply this one. So delta Qj is again, so change, I mean infinitely small change in jth generalized coordinate. Okay, read out the, so derivation if you need. So usually to solve problem, we don't need any derivation. Again, it's little lengthy to prove. So let me do some part of the derivation here, okay? Some part of the derivation here. You can make use that one to prove this one again, okay? So after this one. So usually, so this is equal to, I'm going to transform this part of the equation. Okay, I'm going to transform this part of the equation that I haven't done here, okay? Now look at here, Fi applied force, I'm not going to write A here, okay? I'll just write Fi, but that is applied force. Because forces of constraint we have eliminated in the earlier step itself, okay? This is applied force. Now look at here. So this delta Ri, how can I write that one? So this delta Ri. So since in this transformation equation, what does that transformation equation says? Let me write the transformation equation again. So Ri is equal to Ri Q1, Q2 and so on up to Qn. Is that okay? So then usually the time term will come here sometimes, okay, very rare case. Then delta Ri, I can define it like this. Delta Ri, so that's equal to, so dou Ri divided by dou Q1 into delta Q1 plus dou Ri by dou Q2 into delta Q2 and so on up to dou Ri by dou Qn into delta Q. Now we will not take the time part here. Could have asked question one more. Dou Ri by dou T into delta T. So that is the actually because of the fact that whatever we are taking here, there is virtual displacement, isn't it? Again, read out, virtual displacement is defined as it happens without changing in time. Is that okay? Without changing in time. So that kind of assumption is there. So little difficult to explain that one. Is that okay? Let me try that one again. Is that okay? That's why we are not taking the time part. Okay. Yeah. For a time sake, let me just take only these things. Now look at here, delta Ri, I can write this as summation over j dou Ri by dou Qj into delta Qj, and I'm going to substitute this one into this equation. So summation over Fi dot delta Ri vector, that's equal to, so summation over I Fi applied force usually, okay, dot product with summation over J dou Ri by dou Qj into delta Qj. Look at this one, how we transform this one. So remember, in derivation, similar thing will come, okay? This one and a velocity term like that will come. Again, everything is derived out of this transformation equation and this kind of chain rule only, okay? Derivation runs like that actually. So now look at here. So can I club those summation I comma j? I will run over all possible particles, j will run over all possible your generalized coordinate. Fi dot dou Ri by dou Qj. Delta Qj, can I write like this? Now the technique here is, just make it brief, or you can write last one and you can see the book again, okay? Look at here. So now what I do here is, let me keep summation over j here, summation over I let me take inside. So Fi dot dou Ri by dou Qj into delta Qj. And I call that one as, this is a scalar quantity, Qj into delta Qj. Actually, we keep on doing this kind of thing. So then we can derive our last equation. Now what is our Qj? We call that one as generalized force Qj, that's equal to summation over I Fi dot, let me write it here, where Qj is equal to summation over I Fi dot dou Ri by dou Qj. So we call this one as generalized force. Yeah, question. So delta means actually finite, d means infinitely small, okay? So delta, and so he's asking what is the difference between delta r and dr? Both behaves in the same manner. Again, we are not taking actual displacement here, that's why we are putting in a different symbol, okay? So this is, I mean, I can say like this is larger than this one. Is that okay? I mean, both are very small only, very small change only, but this is infinitely small usually. Is that okay? We think like that in calculus. Again, we need to get into very basic calculus, very pure mathematics to understand this. And it works very similar to dq. Is that okay? It works very similar to dq. Now look at here, this whole thing, this is a scalar quantity again. We are transforming everything into scalar quantity. Now see one thing. We have written this one. Again, this was also old question actually. What is this part? What is this part? Work done. It should be of the order of energy, am I right? And this part should be work done. But this Qj need not be of the order of force. Look at here, something else can happen here. So maybe position or something will be introduced here. So that's why Qj need not be of the order of Newton, remember, I mean of the dimension of force. Is that okay? So now look at here, write one sentence here. So in this one, so usually this is in terms of, I mean this is force, so this is displacement, am I right? And this is total is work done. Here this one need not be in terms of force, this one need not be in terms of position. but product should be of the order of work. Is that okay? Generalized force into generalized coordinate, corresponding generalized coordinate, product should be of the order of force. So write this sentence. QJs, write like this, QJs, I mean plural, QJs need not to have dimension of length, because when we transform to polar coordinate, we got theta and phi, which are not dimension of length, am I right? QJs need not to have dimension of length. Dimension of length. Similarly, capital QJs need not to have dimension of force. Capital QJ need not to have dimension of force. Capital QJs need not to have dimension of force. But capital QJ into small qj or dqj or whatever we write, delta qj should have dimension of energy. They designed one question on this one. And I needed this one also, okay, later to explain. I needed this one also, that's why I just derived that part, okay. And I don't need much part of this derivation. And you should know our aim is to convert, our aim is to transform our coordinate so that there will be no more relation between the coordinate. So there will be no more constraint equation appears again to relate the coordinate. Generalized coordinate need not, so remember, we always start with Cartesian coordinate where everything is x, y, z, all are in length, am I right? When we transform into polar, so only one part is length, so radial part, other two parts are angle, am I right? So that's why, so this is called as generalized force, okay, QJ. So J will run over all possible generalized coordinate, am I right? You can define generalized force corresponds to radial part. You can define generalized force corresponds to theta part. Generalized force corresponds to phi part. Okay, we shall do those things later. Are you getting my point? That is the difference here. So that is the difference here, and we shall see what would happen. Yeah. So usually the next step is, actually this is our actual equation, okay. Our actual equation is this one. So now what we do is, again, if we have conservative force or field, in case of conservative field, what do you mean by conservative field or force? Example, gravitation, electrostatic, like that. Those are conservative fields. So what would happen usually in case of conservative field? Any idea? Actually, curl of your force will be 0. Okay, we shall discuss this one in electrodynamics. Curl of the force will be 0, and work done is independent of the path. That depends only on the end point, am I right? Then this direct consequence of this one is F can be written as minus gradient of some scalar, so that gradient of curl equal to 0. That kind of equation will come. If you know that one, then it's okay. Otherwise, we shall discuss this one in electrodynamics, where V is scalar. We call that one as scalar potential or scalar potential. Usually, whenever you write like this, that becomes potential energy, okay? If you write like this, E is equal to minus del V, I hope you have seen this equation. So, then this V should be potential, that is energy per charge. Am I right? No, not energy per charge. Yeah, energy per charge. So, potential, how to define potential? Energy per charge, like that. Am I right? But we are talking about potential energy here, okay? In this case, we are talking about potential energy. We'll write force, not field. This electric field is force per charge. That's why this should be energy per charge, okay? So, in our formalism, whatever V we write, that is our potential energy, okay? Not potential. Electric potential have got work done per charge, like that. It is defined like that, okay? So, again, this will be very clear after electrodynamics. Now, take it as it is, okay? So, F is equal to minus del V, scalar potential. Now, in this situation, look at here, we can write Qj is equal to, usually our scalar potential depends only on R1, R2 and so on. Number of particles, okay, usually. Scalar potential depends only on the position. Now, what we write again, that scalar potential, we need to write in terms of Q1, Q2 and so on up to Qn, generalized coordinate, by transforming the coordinates. Is that okay? After you write like this, you can write your generalized force is equal to minus dou V by dou Qj. This is similar equation. This is in terms of vector. This is in terms of scalar. We say force can be derived out of scalar. We say like that here. Similarly here, generalized force can be derived out of potential. So, like this, in this kind of derivative. And I think we can show this one, okay. So, from this one, I think we can show this one. By taking that del definition, we can show this one. Okay. So, scalar potential, it doesn't depend on, remember, it doesn't depend on velocity, it depends only on the position or coordinate. Is that okay? So, that's why, again, depends only on the coordinates, not on velocity. Is that okay? Depends only on coordinates, not on velocity. So, that's why, look at here, one more part here. Dou V by dou Qj dot, that's equal to 0. That means V is independent of velocity. We call this one as generalized velocity, okay? Qj dot, we call that one because since Qj is called as generalized coordinate, Qj dot is called as generalized velocity. That's not actual velocity actually, that is related to actual velocity in some other format. You can just see that again part. Which one? F? Which F? So, capital Q? No, whatever the F we have taken, that is Newtonian force only. Okay, whatever Q we have taken, Qj, generalized force, that need not be of the order of Newton or something. Okay, we shall take an example, then it will be clear. This can be torque sometimes. Okay, this can be torque sometimes. When you take angular coordinate, that part of the generalized force will be torque actually. If you take again generalized coordinate as a length, this will be Newtonian force. so that that product is of the order of again work done, I mean energy usually. Okay, we shall take example, then it will be clear. Okay, so F is force only, Newtonian force only. Okay, in terms of Newton only. Okay, so Qj and I mean capital Qj and small qj, those may differ. So I mean it is depending on the situation. Whatever we are doing, that's one, it's a generalization. That's why we are not quoting what is that one. Okay, in case of application you will understand this one. Okay, so again in case of conservative field force, these things will happen. Is that okay? So now look at here. So don't write. Okay, it's very simple. I have this equation again. So J will be equal to 1, 2 and so on up to n. Am I right? J will be equal to 1, 2 and so on up to n. Now what I write here is I am going to write Qj in terms of this one. Just look at this one. Small manipulation in this equation. D by dt of dou T by dou Qj dot. So minus dou T by dou Qj. So minus plus dou V by dou Qj is equal to 0. Okay. Now let me club these two parts. D by dt of dou T by dou Qj dot minus, so dou by dou Qj of T minus V. Is that okay? So T minus V. So that minus of minus plus will happen. Individual derivative. Again, let me do one more part. Look at here. Since dou V by dou Qj dot is 0, let me put T minus V here, no loss. Are you getting my point? Dou T by dou Qj dot, okay, I'm writing it as dou by dou Qj dot of T minus V, because dou V by dou Qj dot equal to 0, no loss. Am I right? Why I can write like this? Because dou V by dou Qj dot is equal to 0. Write the reason. Over. Now look at here. Ultimately, we can write our equation like this: d by dt of. So this one, if I substitute this one, dou T minus V by dou Qj dot minus dou by dou Qj of T minus V, that's equal to 0. In case of conservative field, okay, in case of conservative field, we can write generalized force like this. Is that okay? In case of non-conservative field, you better to use this equation. And now we are going to define Lagrangian. What is that one? T minus V. Again, I haven't defined what is T. What is T? Kinetic energy of the total system. Okay, kinetic energy of the total system. I haven't defined what is T. T is equal to half m Vi square summation H. Again, we need to convert that one into generalized coordinate. Okay, we should not write in our old coordinate. I'm writing that one in a old coordinate. I'm making summation over all particles. Am I right? Particles velocity. We need to convert that one into generalized coordinate. Writing T and V in the generalized coordinate, that will solve the problem 50%. Is that okay? But we need to write T in terms of Q1, Q2 and so on, Q1 dot, Q2 dot and so on, Qn dot. I mean usually it's a function of velocity, am I right? T will be function of velocity. You need to write in terms of generalized coordinate. That's why earlier I told you to derive those things. I mean writing velocity in terms of so in the individual coordinate system. Okay, that will solve the problem actually. We call this one as Lagrangian. Now look at here, usually in Lagrangian, this T will be function of Q and Q dot, okay? Q and Q dot. So you have seen your V theta, that will be R theta dot, am I right? It contains one coordinate, one generalized velocity. That can happen actually, okay? So usually we write it like this, Lagrangian is a function of Q dot T. We will not write J. We will not keep on writing J. Again, so remember how many equations of this kind? J equal to 1, 2 and so on up to n. How many? So that there will be as many number of equations as that of number of generalized coordinate. That much differential equations are there here. Is that okay? So usually we write Q dot T. So T will be usually function of Q and Q dot and T. So usually V will take time independency. It's a function of Q alone. I mean Qj actually, but we simply remove that suffix after that. I mean prefix. I mean this one, index. But actually V is a function of all of those generalized coordinates. We simply write like this. Okay, so this is for conservative field. So that's why I can write like this: d by dt of dou L by dou Qj dot minus dou L by dou Qj is equal to 0. Am I right? In case of conservative field, I can write like this because T minus B we define it as Lagrangian. In case of non-conservative field, you better to write like this. Okay. So use this one for non-conservative field, use this one for conservative field. And we have one special case, our electromagnetic field as well as magnetic field, charge particle moving in electromagnetic field. So that is a kind of, you can't write this kind of equation actually. Okay. But we can define this kind of equation, we shall study that one later, little later. Or better to do it while revising so that you will have some more input from electrodynamics. Okay. We can write similar equation even though that is non-conservative field or velocity dependent potential like that. We are going to define it like that. Okay. But usually now while solving problems we will take what you call conservative field. Most of the case we take conservative field over gravity or something, and in that situation again defining the Lagrangian in generalized coordinate, that will solve 50% of the problem. And look at here, there is no forces of constraint. Is that okay? We don't need to know that one thing. So second one, we need to transform into generalized coordinate, otherwise we can't apply this one, where there should be no more relation between the coordinate. Okay. Yeah. Again, it is second order differential equation. You have time derivative, one more derivative. Usually that will be second order. We shall see that. Now we shall start applying this one. Okay. Yeah. Oh yeah, conservative field. So we will put that conservative field where Qj can be written as derivative of potential. Then we edited that equation like this. In case of non-conservative field, you can't write like this. You have to go for this one. In case of non-conservative field, Qj cannot be written in terms of this one. Okay. But that electromagnetic field is a special case. We shall discuss that one in a different way. That's better. Okay. Electromagnetic field, both electric field and magnetic field, when it exists, when charge particle moves, that should be handled in a different way. That's an exceptional case. So apart from that one, usually in case of conservative field, we can write like this, okay. And most of our mechanics problem, usually gravitation is included. So, or if you take any electrostatic problem, then our electrostatic potential energy included. Potential energy, okay, this is potential energy, you can't subtract something else from the energy. Kinetic energy, potential energy, okay. Yeah, so that's why we will restrict, so now ourselves to that situation, okay. And we can use this one if you have any, what you call, a frictional force that will be non-conservative force, am I right? We can apply this one, okay, we can apply this one even for your viscosity problem. He has done that kind of problem for viscosity problem in our classical mechanics, okay, where in case of that one, that dragging force that depends on the velocity, am I right? And that potential due to that one, that depends on the velocity. Again, we need to, we can make use of this one, okay, in case of frictional force. Now let us start with the most simplest problem, that is simple pendulum. Simple, am I right? No, that is called a simple pendulum, am I right? Usually we will not work with many number of particles, okay, very less case where we work with many number of particles, but whenever we define theory, we need to make it the most general one, okay. Yeah, so yeah, now let me, so what is that one? Simple pendulum. Even though you know everything about this one, now you have to see how this method works here, okay, how this method works here. Now let me take, so a mass m which is suspended, so by a thread of length L, so where this is, I call this one as theta, is that okay? I call this one as theta. Now let me take this one as origin, okay. If I take this one as origin, I can take this one as x cap, this one as y cap. Is that okay? And in that coordinate system, this is x comma y actually. X coordinate is positive, y coordinate is actually negative. Am I right? X coordinate is positive, y coordinate is actually negative. Is that okay? Now, how do you write kinetic energy? Half mv square. In Cartesian coordinate, this is a planar motion, am I right? So, one mass which is moving in a plane. So, planar motion. What you think in the first extent, there is 2 degrees of freedom because it is moving in a plane. But they are related. Am I right? How they are related? So, how they are related? So, what is this one? This is y. What is this one? This is x, am I right? X square plus y square equal to L square. That's your Pythagoras theorem, am I right? So, x square plus y square is equal to L square, am I right? They are related. They are not generalized coordinate and you can't apply your theorem. So, now half mv square in case of Cartesian coordinate, you can write as half m x dot square plus y dot square, am I right? Plus z dot square if you have 3 dimensions. Or I can write this one as Vx square plus Vy square in Cartesian coordinate. Vx square plus Vy square, and I can write that one as half m x dot square plus y dot square. But because of the relation between those two coordinates, we can't apply this one. And what is your potential energy? Mg minus mg into this distance. You have taken this one as the origin. We shall discuss that one, okay? Or when you practice that one, you will understand how to write that potential energy. Potential energy depends on the choice of coordinate. Am I right? And there is no unique choice of scalar potential because only physical quantity is this one, not V. Either if you change V by some constant, then nothing will happen to equation. Can you see that one? If you change v by some constant, that derivative, that constant part will go. That's why there is no unique definition of v. So if you take v and add that to a constant, that's also v, that will give the same answer usually. That's why you can choose origin here. Some people will choose origin at the mean position. So there is no loss, okay? There is no loss. So potential at this point, definition of the potential at this point, definition of the potential at this point, differing by one constant. Is that okay? That will not affect our final equation, okay? So now I have taken origin here. So now according to that one, that's equal to minus mg into this distance. I better to write mod y because I'll always get confusion. If you put minus mg into y, again write y in as a negative value, again what you get? You will get positive. That should not happen, okay? Potential should be negative because mass is downward to our origin. Is that okay? Let me put mod y, that's better, safer. Actually, what is this distance? It is L cos theta. We shall write it later. Why I am writing mod y? Because you may put, when you put y, you may put again negative value. This should be my mg into minus mod of this one, this value. To be in the safer side, I am putting mod here, and it should be negative. Suppose if you are taking this one as the origin, what was this one? It was its mean position. Then mass will be at this height. Am I right? Now look at here. Mass is at this height. Then how do you write that one? How do you write this height? Now from the origin, it is above. You can write mg into h. This height you can write it as, when this mass was here, its length is L. Am I right? L minus mod y. L minus mod y. Suppose if this were origin, your potential will be mg into height. Is that okay? So that will be equal to mg into that height can be written as L minus mod y. I better to put mod y because to avoid confusion, okay? To avoid confusion, I better to put mod y. This distance, so this height will be, this is total length, okay? Total length minus this one, minus this length. You can write like this also and you get final answer same way, okay? But usually I'll choose this way. Usually I'll choose this way. So in some book, I think in J.C. Upadhyay, in some part, he will choose origin here, or maybe in the option sometimes while defining Lagrangian, they may give that option and you should detect that, yeah, so he has taken some other origin. Is that okay? This is by taking this one as the origin. So if you take mean position as the origin, you will get this kind of potential. And there is no unique definition of potential. What is the difference between these two? Look at here. Can you see? Mg into L. One constant is added to this one. That's what I said. These two potentials, they are, again, let me put O here, O dash here, okay? V of O dash, V of O. Now we can't work with Cartesian coordinate. Why? Why? They are related. They are not independent. We can't apply our equation. We can apply equation only when all coordinates are independent of each other. There should be no more relation between them. Is that okay? So now usually what we do here is we will write transformation equation. Okay. Then I mean x equal to L cos theta, y equal to L sin theta, like that. We'll write like this. Okay. After writing, we take x dot. How do you take x dot? L into sin theta, theta dot, like that. Y dot, L into cos theta, theta dot, like that. Then we square and add. But I'll avoid that one because you need to think of generalized coordinate system itself. Okay. Let me do that one. So later, okay. So I'm just trying to introduce in a different way. Okay. I'm not getting into transformation equation at all. Very less case, I'll take transformation equation, I'll substitute that one here, I'll convert this one into new coordinate. Okay. So I want you to write everything in the generalized coordinate, new coordinate directly. So that will simplify this step. So look at here. Now what we do here is we are going to treat the system in the generalized coordinate where r is equal to L, where r equal to L, is it okay? So we can call this one as theta, and I can call this one as initial line. Once you define this one as theta, then this should be initial line, am I right? Initial line of your polar coordinate, and this is your origin. And I have gravity, okay? I have gravity. Is that okay? Now when you go for this coordinate system, now this is polar coordinate system, am I right? This is your, so how you have written in case of, I think I haven't written much thing about polar coordinate. From spherical polar, I went to cylindrical, am I right? This is called as initial line actually, plane polar system, okay? If you take any point, that point should be represented by r and theta. What is r? Distance from the origin, am I right? OP. Is that okay? Theta is angle with the initial line. Now, how do you define r cap? This is your r cap. How do you define theta cap? Perpendicular to r cap. And again, r cap and theta cap will vary when you change the point, okay? Yeah, it's better to have that, have it here. I mean, plane polar coordinate, because we haven't had much thing about that, okay? Plane polar coordinate. What is that one? Plane polar coordinate. So this is initial line. And if you have any point P here, it should be written as r comma theta. And what is this one? This is r, this is theta, and this is r cap, this is theta cap. Plane polar coordinate. Is that okay? Now you can just start from the Cartesian coordinate. X equal to r cos theta, y equal to r sin theta. You can do whatever you have done yesterday. Okay, you can do everything, whatever you have done yesterday. You can define dr vector like that, okay? Ultimately, velocity vector will be equal to, okay, Vr into r cap plus V theta into theta cap. We got the same thing yesterday. We got V pi into pi cap, one more, but we have only plane polar coordinate, okay? That's also needed because many times we work with that plane polar coordinate. Again, that is the generalized coordinate. What is this Vr? Usually r dot. Again, you can show that one, okay? Plus V theta, r theta dot, theta cap. That's your velocity. And what is your velocity square? Vr square plus V theta square. What is that one? R dot square plus r square theta dot square. That's what we need here. Is that okay? How do you write your dr vector? Any idea? I think dr into r cap plus r d theta into theta cap. And divide this one by t, you will get dt, sorry. You will get velocity r dot, r theta dot, like that. Just do that. And in case of spherical polar, you got r square sin square theta pi dot square. One more term. You don't have term here, that term. So that's why in the spherical polar coordinate, if you put pi equal to constant, then you will get plane polar, am I right? Pi dot will be 0 then. In spherical polar coordinate, if you put pi equal to constant, pi dot will be 0, that part will not be there, that will convert to plane polar coordinate, okay? Yeah, we shall see that. We have that kind of problem here, okay? Yeah. Now look at here. How do you write kinetic energy? Now I want you to practice writing kinetic energy and potential energy directly in that coordinate system, not again transforming from this one using x equal to r cos theta, y equal to r sin theta. That's again useless because You should know what are those velocity in that coordinate system. Now look at here, since this mass moves on a arc which is a part of big circle, you will not have this part of the velocity. What is that part of the velocity? So I mean r dot. So if you have any motion here, so what is r component of velocity? This is r component of velocity. This is theta component of velocity. Alright, so let me write that one. This is your VR. Is that okay? So this is your V theta. Am I right? That should be perpendicular. Origin to this direction. R cap direction velocity is VR. Theta cap direction velocity is V theta. Am I right? But look at here, VR equal to R dot. So this length the derivative, but that is 0. Am I right? And you have to think in that coordinate system because we have only 3 coordinates: Cartesian, so spherical polar, so cylindrical, again plane polar is special case. So it's not a big deal. Is that okay? So that's why T is equal to half m VR square plus V theta square in that coordinate system. And we know that and you should know this one also, in this coordinate system, we can eliminate coordinate. Okay, this choice, why we made this choice? Because we can eliminate the coordinate. Okay, that's why it is very important. So yesterday we had that question, what is the choice of generalized coordinate? Am I right? Now look at here. So in this case, half m r dot square plus r square theta dot square plus r dot equal to 0 because r equal to length equal to constant. That is your constraint. What is your kinetic energy? Half m, r equal to length, okay? R equal to length, half L square theta dot square. And we have written kinetic energy in terms of our generalized coordinate. What is our generalized coordinate? Theta. Again, you need to write potential energy also in terms of generalized coordinate, not in terms of x and y. What is this distance? L here, this distance is L cos theta. You can write your potential energy is equal to minus mg L cos theta. Mass is at this much distance downward. This is the origin. Over. What is my Lagrangian? Minus mgl cos theta. Wait a second. Now, so just look at here. We can make transformation like this, okay? I suggest you to write that one directly, okay, in the new coordinate system. But transformation can be done like this. Y can be written as L into cos theta in this one. Because I have chosen x-axis like this, y-axis like this, that's why this happened. It's not just like general x equal to r cos theta, y equal to r sin theta. Am I right? So that's all of our choice. Y equal to L cos theta happened, isn't it? Usually you write x equal to r cos theta. But here my choice of the coordinate y was like this, x was like this. If you have chosen this is x-axis, this is y-axis, then you will get x coordinate as cos theta. Is that okay? So no need to worry, you will get the same answer. Y equal to L cos theta, x equal to L sin theta, right? X equal to L sin theta. So now what is y dot? It will not vary. That's equal to minus L sin theta into theta dot again. Successive derivative. time derivative. Is that okay? So now x dot is equal to L cos theta, theta dot again. Square and add these two. Square and add these two. What would you get? L square outside, theta dot square outside, sin square theta plus cos square theta. What is this one? X dot square plus y dot square. Is that okay? X dot square plus y dot square. What is this part? 1. Am I right? So now, in place of this one, what you have? If you convert half m, x dot square plus y dot square is L square theta dot square. Okay? In a very rare case, we will apply this kind of situation. Very rare case. Where if it is too difficult to directly get into generalized coordinate, we shall try to apply this kind of way. Transformation. First defining everything in Cartesian coordinate, then transforming it into generalized coordinate. Okay? So just have a note down on this one also. Small note. It's not always true that x equal to r cos theta, y equal to r sin theta. Okay? That all depends on how you have chosen your coordinate system. That's our choice always. Okay? But ultimately, you can transform it into new coordinate like this one. Or write it here. So how we have done this transformation? Actually, you would have taken this one as positive x-axis, this one as positive y-axis, then you will directly get x equal to r cos theta, y equal to r sin theta. Isn't it? From Cartesian, how would you go for polar x cap, y cap here, and you will measure theta from this one, am I right? Are you getting my point? So after this class, do this problem, do this transformation by taking, so this is as y-axis, this is as x-axis. So that you can have mass m here, theta here, you will get directly x equal to r cos theta, y equal to r sin theta as your transformation equation. Since I have interchanged that one, I got like this. Is that okay? But it should be of no issue. Okay? So I mean, it doesn't matter. Are you getting the idea? Yeah. So transformation from Cartesian coordinate, our earlier one. What is this one? Y is equal to L cos theta, x equal to L sin theta. So y dot is equal to minus L sin theta, theta dot. So x dot is equal to L cos theta, theta dot. Am I right? X dot square plus y dot square is equal to L square theta dot square. That's equal to half m L square theta dot square. Half m x dot square plus y dot square, that can be converted into half m L square theta dot square. And again you can write y in terms of L cos theta. So v is equal to minus mg, what is mod of y? L cos theta. Actually, this L cos theta will not be negative, okay? And anyhow, why? Theta will be 0 to 90 degree maximum. Are you getting my point? Theta will be 0 to 90 degree. Over. Once we write everything in generalized coordinate, we have only one generalized coordinate theta, am I right? And write your differential equation in terms of theta. Dou L by dou theta dot minus conservative system. Gravitation is conservative. Is that okay? What is L? Plus mgl cos theta, t minus v. There is no other part, r part of the differential equation, because that coordinate is eliminated. Is that okay? That coordinate is eliminated. Now can you just do this one? D by, what is dou L by dou theta dot? Partial derivative with respect to theta dot. You have to keep everything else as a constant, even theta also. What is this one? M L square theta dot square is 2 theta dot. Partial derivative with respect to theta dot. Yeah, what is this one? Partial derivative with respect to theta minus mgl sin theta. Now can you just substitute this one here? D by dt of ml square theta dot minus mgl sin theta, minus of minus plus mgl sin theta is equal to 0. M and L square are constant. I can write ml square. The derivative of theta dot, we write theta double dot. Okay, theta double dot is d square theta dot by, d square theta by dt square, or d by dt of theta dot. Is that okay? Theta double dot. We write that one as theta double dot. One more derivative of already first time derivative. Okay. So plus mgl sin theta is equal to 0. And to make that equation comfortable, we divide by ml square. Theta double dot is equal to, so g theta double dot plus g by l sin theta is equal to 0. Divide whole thing by ml square. Yeah, it is always possible to make it give the velocity so that it will go here above this one. Okay, but when it goes there, what would happen to your tension in the thread? Actually, we don't need those things. Look at here. Yeah, let me just argue that one. Yeah, we shall solve that one. Okay, that kind of problem. I think in a spherical pendulum problem, when what happens when theta greater than 90 degree. Okay. Yeah, so let me just conclude this one. Now what I do here is I am going to take small oscillation. Small oscillation means let me take very small displacement, okay, from the mean position. And in that case, look at here, I can just assume this is almost linear. Let me call this one as x. Not our earlier coordinate system. Okay, I'm not thinking anything. I mean this displacement. I can call it one as x. Am I right? So then this is theta L here. Now what is this x? Can I write x equal to L into theta, just like S equal to R theta formula? Am I right? I can write x nearly equal to L into theta for small oscillation. Small oscillation. When theta is small, sin theta nearly equal to theta, x, so again theta you can write as again x by L. Is that okay? And theta double dot you can write as x double dot divided by L. That's it. Because L is constant. Now when I substitute these two back here, what would happen? Theta double dot x double dot by L. So plus g by L sin theta nearly equal to theta, x by L is equal to 0. That's why this L got cancelled. And that's again second order differential equation. I'm not feeling comfortable with writing in terms of theta. Now what is this one? Harmonic oscillation. Am I right? You can write this one as x double dot plus omega square x is equal to 0. Am I right? Where omega is equal to root of g by L, time period is equal to 2 pi root of L by g. For small oscillation, you can make this kind of correction and you can just have the solution. Remember, if you keep it as sin theta, you can't find the solution actually. You don't have solution for this differential equation directly. And you can solve the differential equation only in case of small oscillation condition. And look at here, how do you solve the same thing in Newton's second law? You need to define tension in the thread, am I right? Theta, T here, T cos theta, T sin theta, mg. Then what would you do? T sin theta equal to mg. We will find T first. Then we will substitute somewhere in other, like that, isn't it? We don't need any of this analysis, vector analysis. We don't need any of those vector analysis. And we don't have to know what is this tension. Is that okay? What is that tension? Actually, that tension, that is the constraint force actually. That made it to move along this one at a constant length from the origin. But that appeared nowhere in our solution.